All right, so welcome to 6.1, which is on decimals and rational numbers. We're going to start at the very beginning by talking about what a decimal is, and then kind of work our way through. So the word decimal comes from the Latin word decem, D-E-C-E-M, and that word means 10. So technically any number that's written in base 10, so the numbers that we use, can be considered a decimal. So for example, like the number 15 is a decimal. Even though you don't see a decimal point, I mean, technically you could write one. You could write it 15.0 or 15.00 if you're referring to maybe $15. But it doesn't, you don't have to see that decimal point. It doesn't have to be written in order for the number to be considered a decimal. So 76 is a decimal, 20.19 is a decimal. However, I would say the word decimal most commonly refers to numbers with an actual decimal point, like 98.76 or 2.35, where you see that decimal point. And then a mixed decimal, the definition of that is just when you combine a whole number and a decimal, such as 29.84. That would be compared to, I'm just going to put versus like 0.84, which would just be a decimal. It wouldn't be considered a mixed decimal. And that isn't anything you have to be concerned about. I mean, like, you're not going to be tested on these terms or anything. It's just good to know what the, the terminology is. There's also, I wanted to mention this too, there are different ways throughout our world that decimals are written. Like in the US, we're all familiar with this way to write a decimal. In England, sometimes you can see that decimal move to the middle, or a comma in some places in Europe, or even a comma, and then the decimal number is raised up top, kind of like an exponent. So there's different ways you can see decimals written. And one thing that's important to kind of go over is just the terminology of decimal places. So for example, like if you were asked in a problem to round to 2 decimal places, what does that mean? Well, you could probably imagine if you have a number like, I'm just gonna add some more digits here, and you're asked to round to 2 decimal places, it just means 2 numbers after the decimal. So like in this number 7.08, there are 2 decimal places because there are 2 numbers after the decimal, and then in 2.5 there is 1 decimal place, since there's 1 number after the decimal. So let's go ahead, and I want you to fill out this chart. This would be a great place to pause the video and you could try this on your own. See if you can remember the name of all of these place values. So you've got this number up here, so 633.71245. See if you can remember the name of all of these place values. And I'm going to go ahead and I'm going to fill them out. So I'm going to start with the easiest one for most people, which is this 3 here, and this would be the ones place. And then we have the tens place, and then the hundreds place. And then after the decimal, we have a tenths place, which is sometimes confusing because if you think about it, so tens place, E-N-S, is 2 away, 2 left of the decimal, yet the tenths place is to the 1 right of the decimal. So you see the word 10 in 2 different places, and they're not, they're different amounts away from the decimal. The next place would be the hundredths place, and then we have the thousandths place, and the 10 thousandths place, and the 100 thousandths place. And then what I want to do is I want to actually write the place value up above the number. So for example, 10, the tens place, that's 10, or 10 to the first power. 100 would be 10 to the second power. 1 would be 10 to the 0 power, because anything to the 0 power is 1. And if you notice, these exponents are decreasing as we go to the right. So 2, 1, 0. And as you might expect, we just decrease it 1 more. So we'll say 10 to the negative 1, which is the same thing as 1/10. And then hundredths place is 1 over 100, or 10 to the negative 2 power. Thousandths place is 1 over 1,000, and that's 10 to the negative 3 if we use an exponent. 10 thousandths place would be 1 over 10,000, and that's 10 to the negative 4. And then last, we've got 100 thousandths, so 1 over 100,000, and that's going to be 10 to the negative 5. So this is going to help us write numbers in expanded form. So we already did some expanded form in chapter 2, but we're gonna now do it again, only with decimals. So let's check out this first example. So we want to write this number in expanded form. So what you're going to do is you're going to take every digit of the number and you're going to write it as that number times whatever place value it's in. So for example, if you just had 633, you've done this in expanded form before, it'd be 6 times 100 plus 3 tens plus 3 times 1. Okay, and now we're going to continue. We're going to say plus 7, so we're right here. We're moving on. That's the tenths place, so it's times 1/10, plus 1 right here. That's the hundredths place, so 100, plus 2 times, that's the thousandths place, 1 over 1,000, plus 4 times 1 over 10,000, just adding a 0 every time in the denominator. And then last but not least, we got that 5 is the 100,000ths place. Now you could also in expanded form write these as 10 to a certain power, so that would certainly be faster. So if you wanted to do like 10 to the negative 1 here, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5, that would be totally okay. So it's either or, whatever you prefer. And then let's write down how you would say this word in this number in words, okay? It's going to be long, but I think it's nice to do this at least once or twice to get familiar with how we say this. So we say this 633, so I'm going to start there. So 633, and so the and is the decimal place. So when you see the decimal place, you just write the word and then you read this entire number. So that'd be 71,245. So I'm going to write that down. So it'd be 71,000 whoops, 2 is not spelled that way, 2 TWO 245. Okay, so we've got 71,245, and then you're going to look at the last place value. So let's count the place values. So it's going to be tens place, hundreds place, thousands place, 10,000, 100,000s. So whichever place value your number goes until, so this would be 100,000s, that's what we're going to write down or say out loud. So it's going to be 71,245 100,000s. That's definitely a mouthful. Okay, so let's try another example. So this would be a great place. Pause the video and try this one on your own. So we're going to write this number in expanded form. So I'm going to say 2, that'd be tenths, plus 8 hundredths, plus 6 thousandths, plus 5 10,000ths. And again, that could be, you could also write it like this. So this is either or, both work. And then in words, everything after the decimal, you're going to say that number as you would say that number without a decimal. So 2,865. So I'm going to write it up here. 2,865, and then to figure out the decimal part of it, you're going to ask yourself, well, what's the last place value here? So tenths, hundreds, thousands, 10,000ths. So it's going to be 10,000ths. All right, so 2,865, actually there's no and there, 2,865 10,000ths without any and. So remember that the and is used for the actual decimal if you had a number in front of the decimal. Okay, so we talked about expanded form, how to write the decimal, where the word decimal comes from. Let's talk about how to draw some pictures. So just like every other section in this class, there's always like a picture or a, block part of it where we can, use a manipulative. In this case, we're going to use, they're called decimal squares, and they can look different. They're all, the outside shape is always a square, but the inside is going to vary just depending on your decimal. So how these work, they're pretty simple, and I'd never used them when I was in elementary school, but when I started to use them as a teacher, the light bulb really went off in my head, and I saw it go off in students' heads too. This really made decimals make sense for a lot of kiddos. So basically how this works, let's start with the first one. So 0.375. Actually, you know what, take that back. Let's start with the simpler one. We're going to start with the simpler one, which is 0.3. I'm going to write that as a fraction. So 0.3 is the same thing as 3/10 or 3 out of 10. And I'm going to actually write it up here bigger. The 10 has to do with the total number of pieces, and the 3 is what we're going to shade. So this is kind of like saying I've got a pizza with 10 pieces and we want to eat 3 of them. So you need to find the picture where there's 10 pieces all together, and it's going to be this first one. So this is 10 pieces all together. So there's 10 rectangles there, and then we're going to shade 3. So we're going to go 1, 2, 3. So this first picture is 0.3, 3/10. Okay, and then next, let's actually work up from easiest to hardest. So the next simplest one would be 0.35. So 0.35 as a fraction is 35 hundredths, and the reason it's hundredths is because it goes out 2 places. So it's tenths place, hundredths place. So that means 100 total pieces in the picture, and then 35 shaded. So we have to find the picture where it has 100 pieces, and that would be this middle one. So there's 100 squares in there. We need to shade 35 of them. So I'm just going to shade, every row is 10. So we've got 10, 20, 30. It's not the neatest shading job, but you get the idea. And then 5. 1, 2, 3, 4, 5. So all together. I'll get a different color. So here we have 35 and then 35 out of 100. So this one's going to be 0.35. And then the last one, it goes out to thousands. So this would be 375 thousandths. I think these definitely, these pictures are way harder. You can see in this last one. So this is actually, these are broken up into 1,000 little teeny rectangles. So you've got 100 of the larger squares, and then each one of those squares has 10 pieces. So 1,000 total. I think this one is definitely harder to count. It's nice if you can blow it up, but it's still doable though, and it makes for a nice visual. So 375 thousandths, we're gonna color in 375. So if each box is 10, let's just count for a minute. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So every single row or column is 100. So we're going to say, okay, there's 100, there's 200, there's 300, and that's 10, 20, 30, 40, 50, 60, 70. So we've got 370, and then we want 5. So I'm going to do half of this next box. And then all of this is going to be filled in. So that's 375 and then out of 1,000. So 375 and then out of 1,000 altogether. So this is going to be 0.375. Okay, and then just to piggyback on that, below we've got another example that is very similar. It's just we're not going to draw the actual picture. So part A, 4,728 10,000. So what would you draw? So we would draw a square where you have, remember the top is always the shaded. So 4,728 parts shaded out of the bottom is always the total. So out of 10,000 parts total. So you could stop the video right now and try the rest on your own. So for part B, we've got a square with 6 parts shaded. So shaded is the top, shaded is top, and total is the bottom, out of 100 parts total. So for part C, you're going to shade 564, so 564 parts shaded out of 1,000 total, because it's tenths, hundredths, thousandths place. So you always go to the place value of the last digit. And then last, we've got a square with 9,754 parts shaded out of tenths, hundredths, thousandths, 10,000 parts total. So another visual that you can use, which is a great one, is a number line. So let's talk about how you could use a number line. So check out this number line below, and we've got 0 here, 0.1, 0.2, 0.3. So every time we go over 1 tick mark on the number line, you're increasing it by a tenth. So that's great when you want to identify, like if I said plot, where 0.8 is, you'd say, oh, well, it's right there. If I said point to where 0.6 is, you say, oh, well, it's right there. What happens when you start to get use more decimal places? So what if I said, oh, well, point to where 0.65 would be? Well, 0.65 is halfway between 0.6 and 0.7, so 0.65 would be right there. Well, what if I said point to 0.655? Then what? Well, it starts to get a little tricky, especially when your number line is like this and you only have it in increments of 0.10. So that's what this picture is trying to show. So let me just show you, for example, 0.372. So here's 0.3, here's 0.4. So 0.372 is in between 0.3 and 4. So let's look at what the in-between looks like. If we put 10 dashes in between 0.3 and 0.4, that would be like 0.31, 0.32, 0.33, 0.34, 0.35, 0.36, 0.37, 0.38. Well, if this is 0.372, 0.372 is going to be between 0.37 and 0.38. So then you'd have to take that increment, so like where you see those arrows there for 0.37, 0.38, and you'd have to divide that by 10. So this is hard to do with the naked eye. It's easy to do a number like 0.5, where's that? But when you start to get up to the thousandths place, it's hard. You need this magnifying glass, which you don't always get. So this picture is just to show you conceptually where 0.372 would be. So it'd be in between the 0.3 and 0.37 and 0.38, and then in between there you'd have to have another 10 dashes, and it would be 2 in from 0.37. So why don't you try example 5, and then I'll do it here and you can come back and check your work. So we're trying to find where these numbers would be on the number line. So the first thing I'm going to do is I'm going to look at what the numbers that are given, and I'm going to try to figure out what these dashes represent. So if there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 between 0 and 1, then I know these are all tenths. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and there you go. There's the 1.0. So if I want to find 0.46, 0.46 is going to be between 0.4 and 0.5. So 0.4 is right here and 0.5 is right there. So 0.46 is going to be a little bit more than halfway. So I'm going to say it's about right there. 1.75. So we've got 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, and then 1.8. So 1.75 would be halfway between those two. 1.75. And then 2.271. So let's try to find out where 2.2 is and go from there. This would be 2.1, 2.2, 2.3. Okay, so we know we're at least 2.1, and then let's find 2.27. So, or I'm sorry, 2.27. So here's 2.2. And then if we divided this up into 10 dashes, 2.7 would be about right there. And then 2.71, we're just going to have to estimate because it's hard to draw 1,000 little tick marks in there. So 2.271 would be approximately there on the number line. Okay, so we're going to use, we're going to combine what we've done with the decimal squares and the place values, and we're going to order these decimals from least to greatest. So this would be a great time to pause the video and see if you can take the decimal that's over here on the left and draw a picture of it on the right with the decimal square. So I'm going to write this first decimal. Notice it's 1.190, so it goes out to the thousandths place. So you could technically write 190 over 1,000, so draw a decimal square of 1,000 and shade in 190. You could also, though, this 0 isn't necessary, you could also do 19 out of 100, and that would be a little bit easier of a picture. So this decimal square over here to the right has 100, so I'm just going to shade 19. So there's 10, and then 19. Okay, so we've got 19 there out of 100, and then 0.036 would be 36 out of 1,000. So remember, each one of these squares has 10 little rectangles. So we've got 10, 20, 30, and then we're going to do 6. So this is 5, and then one of those little bars. It's kind of hard to see, but it looks kind of like that, with that little bar being shaded below. Okay, so clearly this 30.036 is less than 0.19 because the picture is not as big. So 0.195 would be 195 out of 1,000. So we're going to do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So there's 100. And then I'm going to go 9 more. So this would be 190. Be all the way down here. And then 195 would be that top row. Here we go. Okay, so that'd be 195 out of 1,000. And then last but not least, this last one, we could do 200 out of 1,000, or you could forget these zeros and just do 2/10, which would be the first 2 rows. So to order these from least to greatest, one way is just to look at the pictures and try to see if you can tell what picture is the smallest. And it looks like this top one is the smallest because it only has 19 of the squares, or I'm sorry, this one is the smallest for sure. So this one right here, 0.036, is the smallest. And then it looks like this one is next since we've got 19 of the squares. And then this is 19 and like a half of those, so that would be nice. And then this one down here. So just based on that, I could order them. The other way to order them is to write down the decimals. So they're already written for you, but I'm going to write them in these squares so we can really clearly see. Every semester I'll have students ask, how do I put these numbers in order? And one suggestion that I have that works well is to act as if you were alphabetizing. So for example, let's say you had a couple of words like apple and ape. Whoops, starts with an A. Ape. And then maybe Amy. Okay, and maybe I had to alphabetize those. So if I had to alphabetize them, I would start by the very first letter and I'd say, okay, well, all of them have A, so I'm going to move to the next letter. And then here I've got an M and 2 P's. Well, M comes before P, so I would say Amy goes first, and then I take her out. And then I look at these words. Well, if they both have P, then I got to go to the next letter. So this one has P and this one has E. E comes before P, so ape is going to be next. And then apple is last. So same with your decimals. So what you do is you look, I'm going to use a different color. You look at this first digit and you say, what number is the smallest? The 0. So this number is the smallest. That's the least, okay? So then once we have that number eliminated, Then what we do is we look at the other two. So out of the 1 and the 1, we need to know which comes next. 1 is lower than 2. So let's move to the next place value. They both have a 9, so we have a tie. Okay, next place value. 1 has a 0, 1 has a 5. 0 is less than 5. So this number is going to be next, then this one, and then this one down here is last because of the 2. And so that's the order that I have listed down here. So you could use both of those methods. You could use one or the other, you know, just whatever makes sense. It's just nice to be able to kind of go about it in a variety of different ways. So let's talk about what it means to be a rational number. So whenever I'm trying to remember these terms, I try to think of parts of the word so that it's easier to remember them. Rational starts with ratio. And if you think about what it means, think back to the fractions. When you have a ratio, you're just comparing two numbers. So for example, a ratio is a comparison between 1 and 2 and 1/2, or 5 and 6 and 5/6. And you can certainly write the ratio with a colon. Whoop, not 1/2. You could say 1:2 or 5:6, but you don't always have to. So think of ratio as comparison or fraction, and that's really what's describing a rational number. So any number that can be written in the form A over B, as long as B is not 0. Just remember, you can't divide by 0. So example 7, this can be a tricky one. It says convert fractions to a decimal by writing the fraction as a power of 10. So with this first one, this is the easiest because you've already got it as a power of 10, 64 hundredths. So when you're trying to write that as a decimal, what you want to do is do your decimal place and then carry out your place values until you reach this number. So what I mean by that is think tenths place, hundredths place. Okay, stop. And then you're going to write your 64. If for some reason it was like 64 thousandths, then what you would do is you would go out to the thousandths place, so tenths, hundredths, thousandths, and you'd write your 64 as far to the right as you could, and you'd put a 0 in as a placeholder. So look at the denominator, and that will always dictate how many place values you need to go out, and you always shove your number to the far right. So I'm going to erase this since it's not 64 thousandths, it's 64 hundredths, which looks like this. So that one's easy because the denominator is already a multiple of 10. But with 3/8, we don't have that situation. So it's out of 8 and not 10. So one thing you could do, the easiest way is if you have a calculator, you do 3 divided by 8 in the calculator, and you could get the decimal for that, which is 0.375. I'm going to show you another neat way to do this, though, that doesn't require a calculator. What you can do is you can take the denominator and you can make a factor tree to break it down to its prime factorization. So 8 is 2 times 4, and 4 is 2 times 2. So instead of 3 over 8, I could write it 3 times 2 times 2 times 2. Okay? And then we're going to think about what we know about the number 10. 10 is the same thing as 2 times 5. So if I have some 2's, all I would have to do is have 5's for each one of those, and then we would get some form of 10 on the bottom. So what I'm going to do, I'm going to use a different color. I'm going to multiply this fraction by, I'm going to say 5 times 5 times 5. Why 3 5's? Well, because there are 3 2's, and I want to pair up. Every 2 needs a 5 because 2 times 5 is 10. So if you think about this, this is like 2 times 5 times 2 times 5 times 2 times 5, or 10 times 10 times 10. So when you multiply that all out, you end up getting 1,000 on the denominator. Now, if you do it to the bottom, you have to do it to the top. So that's the one downside. You can't just start multiplying multiplying numbers. You have to balance it with what you're doing on the top. So what you can do here then is we can multiply 5 times 5 times 5, which is 125 times 3. That's 375. And then the bottom is easy because the 2 and the 5, those are each 10. So I just need 3 zeros there. So 375 thousandths. Okay, so now this is manageable because I can just carry it out to the thousandths place. So tenths, hundreds, thousandths, and then it's convenient. We've got 3 spaces. So that's where your 375 is going to go. So 3/8 is the same thing as 375 thousandths, and that's the same thing as 0.375. So with the next two, what I want you to do is the same thing. So do a factor tree for 20, do a factor tree for 40. Let's break those down and see if we can get multiples of 10 in the bottom. So let's start with 20, and this would be a great place if you want to pause the video and try this on your own. So 20 is 2 times 10. 10 is 2 times 5. So I'm going to write 20 as, and actually I'll just keep this in blue just like the top. So 20 is the same thing as 2 times 5, and then the top is a 7. So what I want to do is I want to pair up. Okay, we've already got a 10 on the bottom, which is great, 2 times 5, but then I've got this extra 2. So if I multiply that by just a 5, that's all I need is a 5, because then this 2 will go with that 5, and then we'll have another 10, and then I'm going to multiply the top by 5 as well. So we've got 2 and 5 is 10, 2 and 5 is 10, so 10 and 10 is 100, so the denominator is going to be 100, and then 7 times 5 is 35, and then 35 hundredths you write like this, because it's 2 place values, and 2 place values represents the hundredths place. And then lastly, let's do 40. So I'm going to do a factor tree for 40. I'm going to bring this up a little bit. So 40 is the same thing as 10 times 4, 2 times 2, 5 times 2. So 40, we've got 3 2's and 1 5. So these go together and make 10. So we're all set there. And then on the top we have 3. So we have 2 2's that are left over that both need a 5 to go with them. So if we multiply those by 5 times 5, or 25, that means they'd both pair up and make a 10. Then we're going to multiply the top by 5 times 5, or 25. So 25 times 3 is 75. And then we've got 10, 10, 10, which is 1,000. And then 75,000. So let's count place values. Tenths, hundredths, thousands, and then 75 goes to the far right, and you put a 0 in as a placeholder. So let's talk about terminating decimals. So I'm sure you've seen this many times before. What happens if you take a fraction and you divide it in your calculator and the answer keeps going on and on and on and on? So for example, 1/3. If you do 1 divided by 3, you're going to get in your calculator, it's going to say 0.33333. It may at the end say 4 because your calculator just rounds that final number. But that's not an indication of it ending. It's just an indication that your calculator stopped writing it and it's rounding. So what's the difference between a terminating and non-terminating decimal? Let's talk about that. And then how can we recognize what these are if we're just looking at a fraction? So a terminating decimal is a decimal that ends. Okay, so a terminating decimal might be 0.25. So the way that we can tell if a terminating or a decimal is terminating or not is we can look at the denominator and we can find the prime factorization for the denominator. And if the prime factorization of the denominator only has 2's and 5's in it, and think 2 and 5, those make 10. So if they only have 2's and 5's, then we can write it as a terminating decimal. If there's any other number besides the 2 and the 5, then it's going to end up repeating. So for example, this is the way it works out. So you take this number denominator like a 6 and you find the prime factorization. So the prime factorization is 2 and 3, and you can see we have a number other than 2 and 5 there. We've got a 3, so this is going to be a repeating decimal. And you can certainly grab your calculator. Let me see if I can do this quickly here. And you can divide them on the calculator. So we could do 5 divided by 6. And you can see that it ends up repeating because it goes on forever and ever. So that's a good way to just double check. But it's also fun to have a way without a calculator. So for 80, let's do a prime factorization for 80. So we have 8 times 10, 2 times 4, 2 times 2, and then 2 times 5. And so that prime factorization, if you look at all the numbers I circled, are only 2s and 5s. So this is going to be a terminating decimal. So terminating, okay, it's going to end. And just like the last one, we could double check by taking, let me get this in view here, we could do 1 divided by 80, enter, and then you can see it ends. So that's a good confirmation. And then 9/15, so 15, we can take 3 times 5. We've got a number other than a 2 and 5, so this is going to be repeating. And then let's just double check real quick. So we've got 9 divided by 15. Oh, and you know what? I'm so glad I did this. This is a really good one to talk about because this is not repeating. So I just caught myself. And let's talk about why it's not repeating. So we did the factor tree in the denominator and we found that there was another factor besides 2 and 5. But you know what I forgot to do? And it actually has, I forgot to read this in the definition, really important part. So let's just back up a little bit up here. It says if a non-zero rational number, a over b, is in simplest form, and this fraction is not in simplest form, what happens is if you reduce this, so if you take 9/15 and you reduce it by dividing both of these by a common factor of 3, you get 3 on the top and 5 on the bottom. So this 3 here that was in that prime factorization, it ends up canceling out with a 3 in the top, and so it essentially ends up not being there. So we do end up getting a terminating decimal for this one. So let me just back up. So what we should do right off the bat is we should reduce it, and we get 3 over 5, and then look at the reduced version and say, okay, well, if the denominator only has 2's and 5's, which this does, I don't even have to do the prime factorization because it's just 5, then you say that this is a terminating decimal. And as we can see on the calculator, it's terminating. And then if you look at B, that was already reduced, and A, that was already reduced. So I didn't make that mistake on those ones because it just happened to be reduced. So for D, let's also think about that first. So 3 over 14, is there a common factor between 3 and 14? There's not, so I can't reduce that anymore. So I'm going to take 14 and I'm going to do a factor tree for 14. I get 7 and 2, and I end up getting a number other than 2 or 5. So this is going to be a repeating decimal. And then just to be sure, as we saw in the last one, let's see, science standard calculator, we move that over. We do 3 divided by 14, and we end up getting, it looks like 2142857. It looks like that is going to be repeating. And if you look, let's see, it looks like, it looks like we're not, so I see some 2 and 4, 285, so 285, 7143. Yep, it looks like we've got a repeating decimal there. We can't see it. It'd be nice if the screen was bigger and we could see this, but it's a big repeating decimal, so you've got quite a few digits there repeating, but it is repeating. So that's one way that you can, well, two ways. You can use your calculator or you can do a factor tree after you reduce the fraction. Let's think about what the picture would look like. So I'm going to erase these, just the bottom, so that I have a little bit more room. Let's think about 1/3 on the decimal square and what that would look like, and we're going to do this while we do long division. So 1/3 is the same thing as 1 divided by 3. So what we would do is we'd take 1 and we'd divide by 3. We'd write it like this, okay? And so if we take the number 1, 1 can be represented just by this entire square. So think of this entire square as 1. How many times does 3 go into 1? Well, 3 doesn't go into 1. So what we can do is we can divide it into further pieces. So what I can do is add a 0 on at the end. And by doing that, by making it a 10, now I can take that 1, that piece that was just 1, and I can divide it into 10 pieces. So it looks the same, but I'm just dividing it up into pieces. So now we can say, how many times does 3 go into 10? Well, you could break it up into 1, 2, 3. It could go into it one time, 1, 2, 3, another time, 1, 2, 3, another time. So here it goes once, goes in twice, it goes in 3 times. So it goes in 3 times. 3 times 3 is 9. So you can see we've got the 9 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're going to subtract. 10 minus 9 is 1. So if you think about this right here, that would be our leftovers. Well, if you take the leftover, so I'm just going to draw it right here. So if this is our leftover piece, now, if we look at it as 1, 3 doesn't go into 1, but what I can do is I can add a 0 and bring it down and make it a 10, so I can divide it into 10 again. So I can say 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I can do the same thing. How many times does 3 goes into 10? Well, it goes in, there's one group of 3, there's 2 groups of 3, there's 3 groups of 3, so it goes in 3 times. 3 times 3 is 9, and then there's 1 left over. So we've got another leftover. Well, 3 doesn't go into 1, but it can go into 10. So we can take that little leftover piece and we can divide that up into 10. And then we say, well, 3 goes into 10 3 times. So we could circle 1, 2, 3 groups, and then you're going to end up getting 1 left over again. And so this process keeps going and going and going and going. And so that leftover, having that leftover remainder that's not, you know, that divisor cannot go into evenly makes it repeat. So let's just let's do example 9. So we're going to use a calculator now to write the decimal for each rational number, and then we're going to use a bar to show the repetent, so the part that repeats. So let me just pull up my calculator. So 3 11s. So I'm going to do 3 divided by 11. And I'm going to look for the repeating part. So this is way easier than that last one we looked at. So it looks like the 2 7 is what's repeating. So we could write that as 0.27, and you could put the bar over the part that repeats, meaning the 2 and the 7 repeats. So this means 0.27272727. Okay. Next, let's do 5 6. So we'll do 5 divided by 6. Whoops, let's clear that out. 5 divided by 6. And we're left with 0.83333333. So I'm going to write down 0.83, and then I'm only going to put a bar over the 3 part because that was the only part that kept on going. The 8 did not repeat. Okay, so I only put a bar over the part that repeats. And then last but not least, let's do 5/12. So 5 divided by 12. Okay, we've got 0.416, and this is a good one to talk about. Notice there's a 7 at the end. What the calculator does is it actually just rounds that 6 to a 7 since the screen is only so big and it has to stop. There actually isn't a 7 there. It's the calculator rounding it. So the 6's are what repeat. So 0.416, and then the bar is going to go over the 6. So get back here. So 0.416, and then the bar goes over the 6. So now we're going to go backwards. So writing terminating and repeating decimals as a fraction. So how do we write 0.378 as a fraction? So this ends, it's a terminating decimal, and we can just look at the place values. So tenths, hundredths, thousandths place, whatever the number, the biggest place or the farthest right that it goes to, it's actually the smallest place, but the biggest denominator. So tenths, hundredths, thousandths. So we write 1,000 on the bottom, and then 378 is going to go on top. So that's kind of nice. It's really easy to write as a fraction. We don't even need a calculator. We can just count using our place values. The problem though is, how do you do that with a repeating fraction? Think about this one. So this would be 0.3777777. The 7's keep on going, and so if you use my process that I showed you in the first one, that wouldn't work because I told you to keep going until that last digit which is in this case the 8th, identify that place value, and that's going to go in the denominator. Well, there is no last digit here because it keeps on going. So, I mean, what are you going to write in the denominator? A million or a billion? I mean, it keeps on going. It doesn't ever stop. So this, I'm going to show you a technique for writing a repeating decimal as a fraction. So it's going to seem a little bit weird, but bear with me. We're going to use some algebra here, and hopefully after doing a couple, it'll make some sense. So the first thing that you do is you set your decimal equal to x. So you say 0.37 repeating is equal to x. So you write an equation. Okay. The next step that you do, so this is step 1. Step 2 is you're going to multiply by a factor of 10 to get rid of the decimal. Sorry, my writing is so messy with this pen. And what that means is, I'm going to use a different color. You're going to take this decimal and we're going to try to move it to the right here. We're just going to move that decimal so that it's to the end of the number. It depends on the decimal. In this case, that means 2 places. If you have like this decimal down here, that would be 1 place. This decimal down here, we'll talk about that in a minute. But you want to get it so that it's at the end of the repeating part. Okay. And then what you're going to do, so to do that, sorry, I told you to do it, but I didn't show you how. You're going to multiply, in this case, both sides by 100. And by doing that, multiplying by 100 moves that decimal 2 spots over. So what you're going to get is you're going to get 37. Actually, you know what? Let me keep this in blue, and I'll just use green for what I'm doing. So this is going to be 37 point. Now remember, this keeps repeating. So you still have the repeating part. And that keeps going, equals 100x. Okay? And now step 3 is you're going to subtract the original equation. So the original equation, I'm going to do this in green so you can see what I'm doing. I'm going to subtract 0.37 repeating equals x. So the 0.37 repeating, I'm going to actually write it under this part because they're the same, equals x. What happens is the repeating parts here cancel out. By taking something that's repeating and subtracting the exact same thing, then it goes away and it leaves me with 37, which that's my goal, to get rid of that repeating part. And then 100x minus x would be 99x. And then 4, you're going to solve for x. So now you're going to divide both sides by 99 and then reduce if you need to. So x equals 37 over 99. And then just to double check, let's grab our calculator and we're going to do 37 divided by 99, and voila, we get 0.37 repeating. I remember learning about this when I was in elementary school, and I didn't learn this process, but I remember learning that anytime you had a repeating decimal, that there were 9s in the denominator. And I remember thinking, why are there 9s in the denominator? It doesn't make sense. So, you know, yes, it's super easy to just kind of remember, oh, you can stick 37 and put it over 99. But this is a really good way to show why it works. So let's do another example. Example 10a is a little bit harder because you notice there's a number before the repeating part. So what I'm going to do is I'm going to do B first, and then I'll come back and do C. I probably should have put them in a different order when I did the notes, but that's okay. So we're going to follow our steps. So step 1 is you're going to set the decimal 2.7 repeating, and you're going to set it equal to x. And then you're going to multiply both sides by a multiple of 10 so that this decimal here moves to the right hand side so that it's on the other side of the repeating part. So that means if we want this decimal to move 1 place to the right, you're going to multiply it by 10. And if we do it to the left, we've got to do it to the right. So what this is going to look like now is you're going to get 27 point, and then this 7's still there. So 7, 7, 7, 7, 7. You can write it like that. Or if you want to just write it with the bar, then you can do it that way too. And then 10 times x is 10x. Next step is you're going to subtract the original equation. So the original equation is 2.7 repeating equals x. And then we're going to, let's work that out. So the 0.7 repeatings, do you see how those just cancel each other out? Because when you have 0.7 repeating minus itself, it ends up equaling 0. Let me just move that up. And then when you subtract these, 27 minus 2, or 7 minus 2, you get 525 equals 10x minus x is 9x. So there you go, you see a 9 again. So it's not 99, but there's a 9 there. And it has to do with the fact that you're always going to have a multiple of a 10 and you're subtracting an x. So the 10 minus 1 or 100 minus 1, that's where you're getting the 9s. And then we're going to solve the equation by dividing both sides by 9. So you end up getting 25 over 9 equals x. Now it's an improper fraction, but that makes sense because if you think of our original number is more than 1. So if you do 25 divided by 9, you should get 2.7 repeating. And then let's just take our calculator and double check. So 25 divided by 9, and you end up getting 2.7 repeating. Awesome. Okay. Now we're going to tackle this last one. This is a lot harder, and I would say think of this as a challenge problem. You're not going to have a problem like this on the exam, but just in case you're wondering how you would do one like this, notice with this one you've got just a regular number in front, 5. That part doesn't repeat, but the 7-2 repeats. The easiest way to go about doing one like this is just to get rid of that. Move this decimal right off the bat, so that way just the repeating part is after the decimal place. If you look at the first example, 0.37 repeating, that was the case. The repeating part was every number after the decimal repeated. And then the same thing for B, every number after the decimal place repeated. And so what we can do is right off the bat, we're kind of deviating from our steps just a little bit. We're multiplying, what we're going to do is multiply both sides by 10. So we're going to take 0.572 equals x, and we're going to multiply both sides by 10. So we're going to move that decimal. So it's going to be 5.72 repeating equals 10x. Okay, this is going to be kind of like our original equation. So we're going to start here. Then what we're going to do is we're going to say, okay, we're going to follow our other steps. We want to get this decimal over 2 spots, okay? And so we're going to multiply both sides by 100. And by doing that, you end up getting 572.72 repeating is equal to, we've got 1, 2, 3 zeros, so 1000x. Then what we're going to do is we're going to subtract our original equation, but by original I mean the one that we starred, so this one right here. So you're going to say minus 5.72 repeating. The goal here is you want these 0.72 repeating parts, you want those to line up so that way they cancel out. So that's why we had to use this equation and not the original. Otherwise we would have run into issues. So we're going to have 10x over here, and now we're going to subtract. The repeating parts, those cancel. So then you're left with, it'd be 572 minus 5, so that would be 567 equals 1000 minus 10 would be 990x, and then we're going to divide both sides by 990, divide by 990, and then we end up getting 567 divided by 990. So let's go ahead and pull up our calculator, and we're just going to double check that one. So 567 divided by 990 equals, and then we've got 0.5727272, and you've got that decimal. This one is a little bit different than the others. You've got the 9s in the denominator, but there's also that 0. So it's not as simple as just saying, oh, well, we'll just put the decimal over some 9s and call it a day. So because it could definitely vary depending on the type of decimal. Okay, let me get rid of this. There we go. Okay, so we've got a couple more on the next page. We're just going to talk about rounding, and we talked about rounding before, but this these examples we're going to round with decimals. So the same rules apply that we talked about before. You're going to identify your place values. So for this first one, we're rounding to the 10th place. So the 10th place would be where this 2 is. And then you're going to look to the right of the 2, which is where this 8 is, and that's going to tell you whether or not that 2 stays a 2 or moves up to a 3. Anything 5 or greater, you're going to increase the place value you're rounding to. So 8 is greater than 5, or 5 or greater, so we're going to increase this to 0.3, and then everything else becomes zeros. You can also just say 0.3. You don't need the zeros. After the decimal place. This is different than if I said round 283 to the hundredths place. Well, you'd say, well, that's the hundredths place. You'd round it to 3, and then you'd have to put zeros there because 300 is not the same as 3. So if you're rounding and you're on the left-hand side of the decimal place, you do have to put those place value zeros, placeholder zeros. But if you're dealing with decimals, those zeros on the end don't even make a difference. So you can eliminate those if you'd like. Okay, this next one, hundredths place. So we've got tens place, hundredths place. So the hundredths place is that 6 there. You look to the right, which is the 8. That 8 tells you to move that 6 to a 7, so it's going to be 0.07. The tens place is the 6. You look to the right, which is 4. That's less than 5, so you're going to leave the 6 alone and not increase it. This next one, you got tenths, hundredths place right here. You look to the place value to the right. It's a 2, so it tells you to leave that 8 alone and not increase it. This next one, we've got tenths place. So you look to the one to the right, which is 8. That 8 tells you to increase that 6 to a 7, so this is going to become 1.7. And then last, we're going to do tenths, hundredths, thousandths place, which is this 2. We're going to look to the right. It's a 5. A 5 tells us we need to increase that 2 to a 3. So it's going to be 1.683. And again, all of these could have zeros at the end, but you don't have to put the 0. So I hope that helps. Let me know if you have any questions.